Hey, welcome to another coding session. I think I'm going to give a bit of a recap this time for anyone that's new to the series. I feel like I haven't given a bit of a recap for a little while maybe. So we're creating a language called Bangalang. I describe it as a low-level explicit procedural language, a compiled language, and its sort of high-level goal is to make it easy to write some parallel code that you can shift, like you can run it on the CPU, you can run it on the GPU, and it's all very easy to switch between. That's kind of my end goal for this. Right now we're just doing basic language features. So like we can declare a variable, in this case it's an array, so we have arrays. Everything is statically typed. So this is a 32-bit integer array. We can assign, we have procedure calls, and we have, so this here means a pointer to the array, because here's the procedure definition here, which takes the pointer to an array as a parameter. This is how we would dereference an array. And we have auto dereferencing when we try to index an array. So, I mean, what else do we have? A bit further down in this procedure, we have loops, a for loop, well, it's like a while loop. And we have comments, we have if else, just standard if else. So I think we have quite a lot already. We're getting to the point now where we have enough features that I would really like to add some asserts so that I can write like a whole bunch of tests. I mentioned this at the end of the last video. I want to write a whole bunch of tests. So, I added some syntax highlighting. This is not my first attempt at this video. I will say that. So we've already got syntax highlighting for true and false. Then I'll just say like true is not false. And the idea is, if you don't know about asserts, the idea is that if this condition resolves to false, then it will print to the console that the assertion failed and include this message, and then it'll exit the program. So it's kind of used for like debugging and stuff. And then when you do a release build or something, there should be a way to strip these out so that these don't get compiled at all, because they're just kind of development tools. But I'd like to use them as a way of doing tests. So I can write like a whole bunch of different code in my language and just verify that everything is as I would expect it to be, and I think that's going to be really handy going forward. Right. I'm going to put it up here. So the first step I want to do towards that is have Booleans, which is why we already had this syntax highlighting, because I've tried it before, learned a few lessons. So we should be able to declare a bool, and then we should be able to say, I mean, we could do this in one line, but just because I wanted to test the type annotation, and then also an assignment, and then I should be able to like return my bool. That's the most simple first step that I want to try for adding Booleans, and we'll try to expand it a bit from there. So as far as the grammar goes, we have a new data type. So this should be bool, and then we also have a new primary for our expressions. We have identifiers and numbers, and now we can also have true or false. So I'm going to add a Boolean one there, and we will define the Boolean as, we can take that out and make that or, so it's like false or true are the two options. Yeah, Boolean is false or true. Maybe we will, because identifier and number, we've always been too lazy to define. Maybe we'll define at least number this time. Because number, I think, is not so bad. This time we need to do a group. But we can sort of go 1, 2, 3, 4, 5, 6, 7, 8, 9. And it's a group with a plus. 8, 7, 6, 5, 4, 3, 2, 1, 0. Okay, there are some issues there. We're missing some ors. Actually, we're missing or and that slash. Is that all of them? That looks better. So it's a number is a digit, one or more digits. That's what the plus means. Okay. So we have that. We have the data type. That's all the new stuff we added for now. So let's go to our tokenizer. See if we can add it. Oh, sorry. Just before I go further, I just want to, there was a bug that I found after our last video, and I just want to make sure that I nail it. And it's in here. This is when we're doing an assignment and we're evaluating the right-hand side. Well, actually, the main thing is we're evaluating the left-hand side, sorry. So this is auto-dereferencing the left-hand side in the case of an array. And this here is when we don't auto-dereference. But here you can see we use the variable position in the offset, but here we don't use the variable position. It should be like this. So we get the proper offset from the stack pointer. So I just wanted to fix that before I forget. Let's go back to tokenization. So we have a Boolean token and a bool type. That's all we have to do for bool. But for Booleans, we need to something to the bottom. Here we go. This is where we sort of like get all of our tokens that have letters in them. So it could be identifier or keywords or data types. So I think I'll add a new condition in here. So if the token value we found was false or true, we'll do something. And if it's not, then we do these other checks to make sure it's not one of these things. And in this case, we have found a Boolean. Okay, I think that's our tokenization done. So now let's go into parsing. What do we need to change for parsing, actually? We'll go here, see what lines we've changed. We added to the data types. We added to our primary. So a primary can be a Boolean. Yep. So when we go parsing, we parse our primary. Here's the number. So there should be something, I guess it'll be very similar. But now we just say it's a Boolean. I think that's it. We need to add the type. So now we have a node type of Boolean. I think that's about it for parsing. Just parse the Boolean as a different node type. Type checking, I think there's going to be a bit more involved here. So I guess we can go to primary because we have a new node type, right? Yeah, see here's number. So now we have Boolean. So if we come across a Boolean node, then the data type is bool. Yeah. And then I think also when we come up here to our expression, I think we need to say that we can't. I just realized that maybe this should go above, because the coerced type is really the type that we care about. I think. So we need to make sure it's not an array, and we need to make sure that it's a numeric type. Numerical. I'm going to go with numerical. Up till now, all of our types have been numerical. So what I'm saying here is like this expression, we're checking whether it's an add, subtract, multiply, or divide. And if it is one of those, we'll come down here. If it's not, then we just do a primary. So this is stuff for arithmetic, but we can't do arithmetic on Booleans. So we just want to make sure that it's numerical when we come down here. I'm just going to make this utility procedure. If we go back to here, we want something like this. But bool is not included. A number I feel like should be. And it's just like a little convenience procedure that wraps basically a linear search. So we just want to know whether it's found. You know, whether the data type we've taken, if its name is one of these, then we just want to return true, otherwise return false. And I just wanted to wrap it so that I didn't have to deal with these extra parameters. I mean, is that really worth it? Is it? Is it really worth having a separate procedure for that? Maybe it's not. Maybe we just do that. I mean, come on. Is that really so bad? Let's just do that. I feel like it's a bit of a waste to have this. So numerical data types. It feels weird to put it in tokenizations, so I'm just going to put it here for now. I don't know if that's the best place for it, but whatever. Okay, cool. Now when we... Okay, so now we've made sure that we're not going to use bools for these operations. And we've given the bool the correct type information. I think that's it. I mean, what happens if we run that? Ooh, my light freaked out a little bit. Okay. Oh, okay, so we're going deep into here. This is in generation, and it's because we have not added this node. Normally, I'm coming to know now when we get these infinite recursions, it's generally because I'm missing a node, and the default case causes recursion, which is not the best, but not the worst either. Maybe we can make this an immediate. Like this. Well, I think it needs to be a string. So Boolean, if it's true, it's 1. If it's false, it's 0. I think that's fine. Unsupported operation size. That's this. So if we go to here, we're getting the byte size of this data type, which is a bool. And to get the byte size, we look in this byte sizes thing, which we need to add it to. Okay, exit code 0. Was that really it? Let's see, it's after the for loops. There's the for loops, so the next thing should be declare, assign, return. So it's just this here. So we allocate 1 byte, sounds right. We move 0 into it, also sounds right, because it's we said false, right? Yeah, false. And then we return it. Okay. And we get 0. That seems legit. So if we put true, we get 1. Okay. And if we do true plus false, it should be not allowed. It should be not allowed. I thought we checked that. Where is it? Here? Oh, that's like totally wrong. If it's not a numerical type. I said and numerical type should have been or not. There we go. Invalid type bool. 7316, which is the plus. Yeah, so the plus is complaining that you can't use a bool here. Okay. That's good. That's good. Now the next thing I wanted to add is like this, equals equals or not equals. But I only want to support Booleans with it right now, because if I try to support numbers, it gets more complicated, because this expression actually converts these numbers to Booleans, and there's some implications with that. So now I should get invalid token equals. We need to advance our grammar now a bit more. Because to support those, we need to add those operators in here. Right? So we go to our tokenization, and we need a couple more tokens. Damn. Equals and exclamation. I do want to make this lowercase actually at some point. I don't know why I made them uppercase, because I do kind of prefer lowercase. But that's really not important. So if we get an equals, I do have a pattern for this. Here it is. This whole file I want to change. I don't know if I've mentioned that. Maybe I've mentioned it many times. One day I will change it. But this pattern here is like, you know, we found an equals, and then we check the next character. If that's also an equals, then we found an equals equals. Otherwise, we fall back just to a single equals. And then we kind of want something like this. So this says if we have 2 more characters, and the first character is exclamation and the second character is equals, then we have exclamation equals, right? So I think that's taking care of our extra operators tokenization-wise. When we go to parsing, okay, so when we do parsing, where is it? Oh, it's above where we are. Here. So this is the operator precedence, the precedence climbing algorithm that we did a few videos back, and we have a few sort of helper like utility procedures that we need to update to handle the new operators. And it should just be a case of updating these helpers and then everything should work, I hope. I was looking at the documentation for Odin, and I found you can just do this. So you can list a set of cases and all of them will go in here. I think that's really nice. So equals equals and exclamation equals get added to the list. They're considered binary operators now. We can do something similar here to what we did before. And we're going to add another level and bump these up. And that's kind of in line with Odin. It's operator precedence. We'd only been working in these two levels before, and now we have this level, which is a lower precedence. So that's why I put it 1 for them. And then this is just a map. A map from token types to node types. And it's only used for binary operators at the moment. Could potentially expand its use maybe at some point. So we have 2 more node types. And I think that should be it for parsing. I think that's all we need to do for our new operators. When it comes to type checking, so now we need to expand this check, right? Because we can allow non-numerical data types to do binary operations. We just have to restrict which ones they can do. And so we have this list here. Let's add to that list equal and not equal. We also, sometimes I quite often forget to do this, so maybe I'll do it now. We also have to add it here in generation because it has the same kind of pattern. Let's keep a copy of that. So so if it's a numerical type, we'll just say in general it can't be an array. And then on top of that, if it's a numerical type and we're trying to use equals or not equals, that's not valid. Okay. We'll remove this later on because we do want it to be valid. Numbers, you should be able to test equality and non-equality of numbers. But like we said before, we're not going to do that yet. And if it's not numerical, let's be more specific with this. If the data type is bool, and we're not using either of those, that's also wrong. So Booleans can use these two, numerical can use everything else, but not these two. So those are I think that's kind of the only checks we need to add, right? Maybe not. Maybe there's more we need to do. So we've grabbed invalid type. So it's probably one of these, right? That is triggered. So it seems like we're trying to use we've got an equal, and the data type is bool. Oh, wait a minute, I think I've got these expressions wrong. So if it's a numerical data type and it's one of these, then that's a problem. Okay. So that's actually OR. If it's a numerical data type and it's this or it's this, that's a problem. Okay. If it's a Boolean and it's not this and it's not this, that's a problem. Because we have a Boolean and we have equal and that's all good. We shouldn't be complaining about that. Okay, we have an invalid node at line 73. Failed to generate expression. Okay, generation. Okay, yeah, because we don't have the node for this. So we need to add a couple more of these for equal and not equal. And then we have to figure out, how do we do that? So I think what we need to do is we need to have, I think, two operations here. First, we need to compare the left-hand side, copy to register. I feel like this is a very much for these ones. And maybe we'll just go final dest. Yeah, this is something I've been thinking about before. Like for these ones, it's necessary to make sure we're in a register first. But for this one here, we know we're moving into racks anyway, so it's not like a big deal. And then for these ones, I feel like maybe we need to do something separate. So when we compare left and right. So let's say equal compare and equal. So this is the one where we create our Boolean, or we set our Boolean. And to do that, I found some instructions in here. This instruction listings has been quite a handy page actually recently. So there's this one here, set CC, this instruction, set byte to 1 if condition is satisfied, 0 otherwise. So that sounds like our Boolean, right? It's setting a Boolean based on a condition, and CC is the condition. And I found down here that there are these conditions in this table that you can substitute with CC. We have equal, which is E, and there's not equal, which is not equal, NE. So for equal, we set E. So if it's equal, it'll set this to 1, and if they're not equal, like it's based on the previous comparison, right? This comparison will set some flags, and then here it'll check the flags to see whether they were equal or not. And if they were, it will set this register, our final destination, does it have to be a register? Well, I guess we'll find out. This final destination will become, 1 or 0 based on what we did. So maybe we'll just copy and paste that, and we'll just go not equal, and it's just NE. I think that's the, is that all there is to it for the assembly? Maybe get exit code 0. We had true equals false, so we should get a comparison between 1 and 0. Let's see now, where are we? After the loops, here we go. Yeah, compare 1 and 0. And so we allocated our Boolean, we compare 1 and 0, we set the Boolean we just allocated to 1 or 0 based on the result of the comparison, with if they're equal or not. Then we return our Boolean. Let's try that. Invalid combination of opcode and operands. Line 157. So this one's not happy. This one is happy, so this one can take a memory address. And actually, this is one of the things I like about this table, because I can see here actually. It's R/M8. So R is register, M is memory, and I guess 8 means 8-bit. So this means that the argument to setcc can be a register or a memory address. I'm using a memory address. But let's see what we can do with compare, because it seems to be unhappy about that. It's probably near the top. It's quite a standard one. Here we go. So it either can be a register on the left and a register memory or immediate on the right, or it can be a memory on the left and a register immediate on the right. So it can be immediate on the right, but not on the left. These are both immediates. So this one is not allowed to be an immediate. So I guess we're actually going to do this here as well. Copy to register. Yeah, so that just makes sure it's in a register. Maybe I should have just left this out here. It's a bit redundant for divide, but it's something we can clean up later. Because it really seems to be needed for most things. Well, it is a bit different actually, because this one, it's the left-hand side. This one, it's the destination. But here, it's really not the destination that we want to override. It's the left-hand side, right? We want to make sure that's in a register. So maybe we just need to go like left-hand side dist. Oh, not that one. Yeah, I think that's what we need to do. Make sure the left-hand side is in a register. Yeah. Okay, so yeah, now we've put it into a register so that we can do the compare. And then we set. So should be happy with that. And we get 0. Nice. Nice, nice, nice. And if we go true equals 3. Excuse me? That should not succeed. So this is where we do the check for compatibility, and it seems like it passed. Okay, so number is the second one. So we've got Boolean, number, and then the expected type is Boolean. But we ignore Boolean. We just say, oh, Boolean. I mean, we ignore number. We just say number. Great. Yeah, number's always good. So I think we need to improve this. I think we can simplify this condition a lot because I figured out that you can just do this. If that's not equal 0, that's testing whether it's defined yet or not. I also think we can do this. Here's an idea. We just take the first one and put it in here. And then I think we can do this. All right. So the first of the data types we put into here. And then we loop through starting from index 1 to the end. Since we don't put a number here, it goes all the way to the end. So we loop through the rest. For starters, we need to take that off. Okay, and then maybe if the original type, so if the new type is empty, we don't care about it. We don't want to know about empty types. If the old type was empty and we've established the new type is not, then maybe we just grab the new type and continue. We don't really need to test any further. We know that's not the case. I think it's not quite this simple. Let's instead say if they are equal, there's nothing to do. Yeah, it means that yeah, if they're the same, what to do. And now we can say if the name is equal, that's bad. So because we've established that they're not equal, the data types, so if the names are equal, that means that something else is not equal. And if anything other than the name is not equal, so at the moment that can be the length, so whether it's an array or not, or how long the array is, and it can be whether it's a reference or not. If those two things are different between the types, then it's a no-go. They're not compatible. And then I think we need to do something. So if the data type name is number, we need to do something so we upgrade from numbers to something else. What did we say? Is it down here somewhere? Where did we put that? Didn't we make a helper? Oh, that's right. We didn't make a helper. We just did it inline. Where did we do it? Here. I want to copy this. Actually, it goes here. So if the new one is a number and the old one is, a numerical type could include number, but we already know the names are not the same. So that means that this must be one of the other ones, which is a complete number. So in that case, they are compatible, but the coerced one is already the one we want. So we just skip. And then there should be the other way around. Like that. So if we had a number and now we get something better, then we want to upgrade, right? And I think after that, it's just, if none of these checks have worked, then it means we have something where the only thing different is the name, and the names were not compatible. Yeah, so it should be false. I think that's a better... Okay, bool, number bool. Oh, that's right, that's right. That's right. That's right. At first I was like, oh no, we still have an error. But we intentionally wanted an error. Okay. Did we actually test it, that it ran and gave us the answer we wanted? 0. Yeah, because it should resolve to false. And if we do that, we get 1. And even it shouldn't be because we called it true. Like if they're both false, that's also 1. Nice, 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 nice. All right. Wow, cool. Okay, I'm really happy with that. I think that's as far as I want to take Booleans in this video. The next thing will be, yeah, to actually use numbers in the equality check. And maybe we can even do like greater than and less than as well. But that's a bit more involved, so I don't think we have time for that right now. We do have a bit of time left though, and there is one thing that I've been really wanting to do for a while. So let's see if we can tackle that. It's totally unrelated to everything else. It's in the main file, which we barely touch. I'm sick of doing this every time, right? You notice that I do like 4 commands every time. And I want this to do it for me. I did have a play with it before, and I did some research and stuff into how to execute something, like execute a command line program from Odin. And I remember it was like a whole mouthful, so let's see if I can figure out how to repeat it. I want to say U32 was the return type. Why are some of my files indented with 2 spaces and some are 4? I like 2 spaces. I want them all to be 2 spaces. This is nice. Okay, anyway. Just a little gripe. So I think it was like a system dot something or libc.system. I think that's what it was, and I have to import c//libc. Is that a real thing? Yes, so you pass in the command string and you get an int back. But the int you get back is not the correct int. So you need to convert it with this like Wexit something. What was it? I think this is like a Linux thing, you know. I think Odin does just a very light wrapper on the Linux system calls. So I mean, if I go to Windows, I'm going to have to do something different. But there was some Wexit, Linux Wexit status. Oh, POSIX as well. I guess it's a standard. But I think you have to do like this, and it will convert it. I think it was something like that, and then I think the import was syslinux. But this takes a U32, so we need to convert. Oh, that's right, and system actually takes a C string. So you have to, there's like a clone to C string. See, what a mouthful, right? That's how you execute a program and get the exit status of it back. Wow. So we want to execute these programs. So I want to have like a build proc and a run proc. I think I'll also make like a compile, which does what we already do. So compile is kind of all this stuff. Let's put failed to type check in here. And let's pass in source path and wow, where did that camel case come from? You get out of here. Okay, and the ASM path. So we put the ASM path there and the source path there. And to build, first we compile. So we build a source path, right? I guess we just have a source path and a bin path. So this is like overall a build should take in a source file, an output, and executable. So the bin path is the executable. So the ASM path is concatenation of bin path and .asm. And then we want to do our execs. So we exec I guess we have like a NASM command, which is also a concatenation. Yeah, I think so. So this is our NASM command. But we want to substitute some stuff in here, like this is the ASM path. And then there's also this path, so this can be the object path. Oh, whoops, that should be the thing, but then it should have the extension O. Like that. And we execute that command. So yeah, build is compile, assemble, which should give us a code. And we want to say if NASM code is greater than 0, then we have yeah, something like this. Well, I guess we exit with the code that it gives us. And we say, oh, I guess we need to cast that to an int. Failed to assemble. And then we want to do the same thing again for the linker, for LD. And failed to link. Except now we take this command, so that's LD object path bin path. Yeah. Okay, cool. So that's how you build. You compile, you assemble, so you run this command, then you link, so you run the second command. That's a build, and you end up with your executable. Then if you want to run, I guess this will also take in both of these. So first you build, and assuming that was successful, you do something like this again. But now we're running our actual program. I think we don't need. Well, I think we just want to return the exit code regardless. Do we need another bracket or something? Yeah. I guess it's just bin path. Like that. And I still can't be bothered doing parameters because we always want to build the same thing, so whatever. But let's see what it was. So this was our, we can probably just do that. That's our source file, and our out file is bin, and let's give it the same name, example01. I think that's it. Like I say, I had to try this before, so I had figured this out. And once that's figured out, like the rest of it's not so hard, right? This is the code we had already. And then it's just a matter of running these commands and grabbing the exit codes and exiting with them if they're above 0. So now if I run, process finished with exit code 1, which is what we're expecting, right? Because they were equal. So if I change that to true, now I just have to go run and we get 0. Or I can take that away and now this should exit with 5. Yeah, so I mean, that is so much nicer not to have to run all those commands. Take me way too long to get to that, I think. But I'm stoked we're there now. We do still have a bit more time. I'm just trying to think now, is there something else that I had been thinking to clean up? I feel like there were a few things in generation. I think I wanted to have, I've got these register things. It's like a convenience for making a register location. I think I wanted to do the same for immediate and memory. So it's kind of like name and offset, and the immediate is just has a value. So then that would be immediate, convert the value and 0. So int to string means that we need strconv I to A, and we just need to have like a little buffer. 8-byte buffer should be plenty. We're not going to have giant numbers here, right? And that needs to be a slice. I've done this a few times now, so I remember how it works. And here, so it's like the address. There's like an address and an offset. So this one actually uses the offset, and then there's the address. So it's just, I mean, they're just like really basic convenience functions. but I think it's nice. So now I can have a look around for wherever we use that. And then we can just go memory RSP thing. So it's a little bit nicer. A little bit. It's not like amazing, but I think for the immediate it's nice. Should go like that because this is immediate. Like for this one, we can just actually put the value in. Oh, but sometimes we have the string. So maybe we can do immediate string and immediate int. And this one we just put the value straight in, and then we do the same as this. And then that should be happy. So we've overloaded it. I said that should be happy. Redeclaration of immediate in this. Oh, okay. Now it's happy. So let's continue with our memories. Memory, blah, blah, blah. Memory. Memory. Got quite a few more here. Hey, I didn't want to bookmark that. Like so. I think this is just a little bit nicer. I think I do have a whole list of things actually. That's right. Here. So we've done build, run, intermediate proc, immediate proc. Well, I've done immediate and memory. I also wanted to do alloc and dealloc, and maybe ref and deref. Just encapsulate a few things. So we've got a few more minutes. Let's just see how far through we get. Oh, here's another memory. So now let's search for immediate. I think that's not used much at all. Oh, we already fixed up two of them, didn't we? So that's immediate 60. All right. So that's that one. Alloc and dealloc. I think those are nice ones to have. So allocate and deallocate. So I guess it's kind of like a size, and we need the context because we'll be modifying the context. And it's kind of anywhere where we use RSP sub. No, sub RSP. Sub RSP, that's an allocation. So allocations look like this. So we also need the file because we're writing assembly. So we're allocating on the stack. And then deallocate is just the opposite. We're just adding and subtracting, like so. So anywhere we see sub RSP, we can say allocate file, and we need the context and the size. Is it run the other way? Let's run the other way. Yeah. So that's allocate, and then down here looks like there's a couple more. Param byte size. I think that's it. And return byte size. And this is where we deallocate the call stack size. So that's add RSP. So there's one other place up here where we do it also with the scope stack size. And that's unhappy because it needs to be the scope context. Wait a minute. Huh, we never actually update the thing. I guess it doesn't really matter because this scope is never actually going to be used after this. You know, we created it for here and then it gets discarded. So it doesn't actually matter. Okay, expression syntax error on 183. So what did we do? Oh, sorry, this is out.asm, which is not, we don't use those anymore. It's this one. 183. What the hell? That's some garbage right there. That's the return. So that's an immediate of 60, I think, going into EAX. Let's go to our return. It's this here. No, this here. So on the left-hand side is an immediate of 60. That's where we're copying from. Yeah, so it's this one. So that immediate did not work. Huh. Value 1, value 0, value 60. So if I step out, well, I guess we never get to see it, do we? This is what you get for trying to just do one extra little thing at the end. It breaks, of course. If we step out. Oh, that's right. We need to find the 61. There's the 61. So let's step over. And blah becomes 60, right? Maybe it's like an allocation thing. I've always found it a bit strange, this whole setup here, because I'm like, this buffer does not get persisted, right? So maybe this is actually not such a simple thing to do, unfortunately. So this is like exit. So if I do that instead, we still get 183. We still get that. But if I go here, skip that, we go here, we step in. Oh, that's register name, so step out of that, then step in. So this is our copy, and our source is length 2, but it's like an empty string. Okay, maybe the immediate is not worth trying right now. Or maybe we'll just do it with a string for now, just to keep things simple. So we'll just go like this, immediate 60. And then down here, I think I'm just gonna do that. Yeah, they're not amazing. It works. Okay, slightly better-ish, maybe. But this here, this main, how I can just press play and then I get my exit code, that is much better. Okay, enough for today. Thanks for stopping by. Have a good one. I'll see you next time. Ciao for now.